Today we want to continue finding volumes of solids of revolution, mostly because we're taking a little detour off of the calculus train and hopping back onto the analytic geometry, doing some analytic geometry. The main advantage that I have, the main thing that I like about this problem is that it works with something very familiar, just a parabola. But I turn the parabola sideways. So rather than having y equals 6x minus x squared, I just switch that around. X equals 6y minus y squared. This doesn't happen a lot. Most of the time we make functions of x. Most of the time because if we're setting things up, that's how we set things up. We set our independent variable horizontally. But this being math class, we want to be more flexible about the things that we can do. So I'm just taking a simple thing, parabola, and turning it sideways by switching the x and y. So we flip our parabola around the line y equals x, and this is what it would look like. All the same stuff happens. So we can see that if x is equal to 0, then y is equal to 0, and y is equal to 6. Those are the two zeros. If we think about the zeros on the y-axis, the two y-intercepts when x is equal to 0. So this tells us certain things. This tells us that our vertex is going to be halfway between, vertically anyway, halfway between 0 and 6 at 3. And if we plug 3 into our expression, we get 18 minus 9. That tells us that the vertex is at 3, 9. So because of what we plan to do with this problem, it's going to be convenient for us to rewrite this problem rewrite this parabola in its vertex form. So rather than 6y minus y squared, since we're going to want to solve for y and get these two functions of x, we're going to write it in its vertex form. And the best way to get things into vertex form is to avoid completing the square if you can, and just find the vertex. So since the vertex is at 3, 9, we'll have y minus 3 squared plus 9. Always avoid completing the square when you can. If you can't avoid completing the square, then complete the square. Oh, there is an instance where you should complete the square and not avoid it, and that's using the quadratic formula. Just complete the square. That's what the quadratic formula does. Anyway, every time you use the quadratic formula, you're technically completing the square. Just complete the square. That way you don't have to remember the stupid formula. And we say it wrong every time we say it anyway, so let's just abandon that. So we're going to take this region and we're going to rotate it around the axis, x equals -2. So I've got all the complications on this one. I have turned my function sideways. X is a function of y rather than y a function of x. And my boundary is not, my axis of rotation is not a boundary of the region. And that's why we get a solid that has a hole in it. So we're kind of getting this donut shape, but it's going to be perfectly cylindrical on the inside, and it's got these parabolas on the outside. This is similar to the Trade Federation ships in Star Wars, a Phantom Menace, the Phantom Menace, but without the big old gap in the front. Or if you don't like Star Wars, you can think of it as a very strangely shaped donut. Or I could mention that it's kind of like a modified torus. Not torus like Ford Taurus, but torus like a circle rotated around an axis. But it's not a circle, so it's not really a torus. But it's not really a donut either, so I don't know. And if you know the word torus, you know that you don't have to concern yourselves with what the shape actually looks like. Anyway, we're doing a volume of a solid of revolution, and we have two strategies for calculating this volume. We can either slice perpendicular to the axis of rotation, or we can slice parallel to the axis of rotation. Since the order that we went was slicing perpendicular first, that's what we could start with. So slicing perpendicular to the axis of rotation would mean slicing this direction. Since the axis of rotation is not a boundary of the region, we know that we're going to have a volume of the slice as pi times r squared minus r squared times the delta variable. And in this case, since we're slicing in this direction, our delta variable will be delta y. So we should identify where the slice is. So here is where the slice intersects our curve. So we should label what x and y are. So here's x down here. Since we're on coordinates, we don't get to choose where x is. We don't have to choose where x is. And we also don't have to choose where y is. Now that we've labeled x and y, we know that our volume of the slice should be pi r squared minus r squared times delta y. I need to identify big R and little r. Anything that in a solid revolution, anything that you're going to call a radius is always measured from the axis of rotation. So big R is from the slice to the from the axis of rotation to the far end of the slice. I know I should have drawn it lower. Big R goes to the far end of the slice, and little r goes to the near end of the slice. So we need to write our two radii in terms of y. We're just following a playbook. We're just following steps. Once we've drawn, the steps are, to reiterate, once we've drawn our region, we make a decision about how we're going to slice, and then we write down the formula for the volume of the slice that we know we're going to be using. Then we need to draw a representative slice inside the region, identify x and y, the variables that are going to be in play, and then we'll identify the dimensions that are specified in your volume of the slice. So I need a big R and a little r. Little r goes from the axis of rotation to the near end of the slice, which is always on the y-axis. So it looks like little r is always equal to 2. Big R goes from the axis of rotation across this gap and then all the way through the region. And so it goes 2 plus the x. So big R is 2 plus x. But this is no good. I don't need these r's in terms of x. I need these r's in terms of y. Fortunately for our heroes, we have an equation relating x and y. I can replace x with 6y minus y squared. So big R is going to be 2 plus 6y minus y squared. So now we can refine the volume of the slice to be pi times big R squared minus little r squared times our delta variable. Just following steps. Draw your region, decide on your slicing strategy, label the variables, label the things that you need for your volume, write the things that you need for your volume in terms of the variables, the delta variable. At this point, we've done the analytic geometry part. Now it's time to do the calculus part and set up the definite integral. So our total volume let's see, I'm going to factor out the pi. And then I'm just going to leave this. I don't want to square this trinomial, so I'm just going to leave it. 2 plus 6y minus y squared. I will square the 2. That I can handle. Our delta y, our discrete delta y should become the continuous dy. Now we need to integrate over all the values of y that are in play. The lowest value of y that corresponds, that we'll see in this region is 0. And the highest value of y that we'll see is 6. If we were going to do this integration by hand, then we would want to square that polynomial. But since we are armed with a calculator, we're not going to mess around with it. We're just going to math 9 our way out of this. So we'll math 9, 2 plus 6y minus y squared minus 4 with respect to x from 0 to 6. Forgot to multiply by pi. So 403.2 pi. So 1266.70. Oh, 1266.7, because I usually request 5 significant figures. I wouldn't mark it wrong if you made this weird fraction, 2016 over 5 times pi. That's the exact answer. But since I requested the approximation, just give me the approximation. Whatever you do, do not mix a decimal, write a decimal multiple of pi. I don't know why I don't tolerate that shit, but I won't tolerate it. So if you're like, oh, 403.2 pi, I was like, get out. You write that down on a test or something, I was like, get out. If you put it on Canvas, I'll say, are you sure about that? And you're like, oh, yeah, then I'm like, oh, I'll just shadow drop you from the class. It's like, oh, why can't I log in? And then you send me an email and you've been blocked. I'm just kidding. Just multiply it. If you're gonna use a decimal, just multiply it. It's worse if this decimal wasn't exact. If this is like 1/3 pi and you put 0.333 pi. At that point, I'd probably just try to make arrangements to have you, expelled. I'm just kidding. Strangely enough, if you take the 2016 divided by 5 and write it as a mixed number, and then try to slap pi on that, also no. So what was it, 403.2? So if you try to write 403 and 1/5 pi, this is just completely unacceptable. Because this is a demonstration that you don't know how numbers work. When you write the number in front of pi, what's the operation? Multiplication, right? So 403, then the 1/5, is that being multiplied? No, that's added. That's 403 and 1/5, 403 plus 1/5. So you write this, only the pi is getting multiplied by the 1/5. Or should we make a convention where the 403 and 1/5 is treated as one mixed number, so there are implied parentheses around the 403 and 1/5. Either way, this is terrible. Absolutely don't do this. Heck no. So that's just bad. Either write a fraction times pi if you want to be exact, or just give an excessive amount of significant figures. Now, I realize there are some professors that are going to be watching this video. I'm just kidding. No professors are going to be watching this video. Some other instructors are going to be like, oh, what? You are an insane person. 403.2 pi is perfectly acceptable. What's unacceptable is asking for 5 significant figures. All of this is beside the point. I asked for 5 significant figures because it's the easiest thing to check. So all you chemistry professors, don't at me. Get out of my comments. Oh, let's try to turn comments off. Any questions? The complication here was that our axis was not a boundary of the region. And so we had to do the complicated washer version. We had to come up with 2 radiuses, 2 radii. But just like skywalkers, we have another technique. Here we sliced perpendicular to the axis of rotation. And so we use washer. We can also slice parallel to the axis of rotation, and that would use cylindrical shells. I'm going to draw a modified version of this with not all the, no, I'm going to run out of space. In my mind, I was just going, I'll draw the other slicing on the same picture. And then the other half, the rational part of my mind said, are you insane? No, do not do that. Just draw it again. And I was like, oh, but I don't want to draw it again. Then the rational part of my mind saw the truth, said, yeah, you do. Well, you're right, it's kind of fun. So step one complete. Draw your region and your axis. We don't want to have to try to draw the entire solid. If you can draw the entire solid, that would be really cool, but it's not exactly helpful. Because we're trying to find volumes of things that we don't have standard formulas for volumes, like a torus or something like that. Once we have our region and our axis drawn, we decide on a slicing strategy. We've only got two to choose from: slice perpendicular and slice parallel. We've already done slice perpendicular, so we're going to slice parallel. So I got a vertical axis of rotation, so I'm going to draw a vertical slice. What that means is that we are deciding to slice with a delta x. So by making this choice, we have chosen delta x as the variable, or as the delta variable. Once we draw our slice, we should label x and y at the intersection of the slice and any functions that are in play. So here's where the slice impacts the functions in the x direction. So here, I will label x. And we notice that there are two different y's. So I will label them separately rather than with a bracket. But I want to label any x and y where the slice intersects any graphs that are in play. As soon as I drew the non-invertible part of a parabola, you knew that these two y's were going to show up. That's why I picked the non-invertible part. But we're not there yet. We have chosen the slicing strategy parallel to the axis of rotation, so we can immediately write the volume of the slice is 2 pi times the radius times the height times the delta variable. Once we write down our volume of the slice, we know what we're looking for. I need to label a radius and I need to label a height. Radius is always measured from the axis of rotation to the slice. So radius is from the axis of rotation to the slice. Notice that I just have one radius because we're slicing shells and not washers. Height in the shells case is always perpendicular to the radius. Now we have finished with the diagram part. We drew our region and our axis. We chose our slicing strategy. We drew our slice. We labeled intersections of the slice and any functions with x and y, and we wrote down the volume of the slice. Then we identified the pieces of the slice, labeled the piece of the slice in our diagram. Now I need to write all the pieces of the slice. I need to do the development phase. All the parts of the slice, I need to write them in terms of the delta variable. So R, we can see, is from the axis of rotation to the slice. The slice always has the same x. So it starts off here at 0 and then goes up to 9, but it's always that one x value determining the slice. So our radius R is just 2 plus x. 2 for the gap plus x to get to the slice inside the region. Since our delta variable is delta x, this is what we wanted. In the previous problem, we had to trade our x for an expression in y because we had delta y in the previous problem. This is delta x, 2 plus x is what we want for the radius. Our height is the difference in y values. It's y2 minus y1. So I need expressions for these two y values because I need the delta, because the delta variable is delta x, which means I need to turn my equation around. I need to adjust. I need to solve this function for y. So first we'll subtract 9. I'm going to change the signs. Now we can see where the two y values are going to show up because I have to undo the square, which produces a plus or minus. So the two y values are 3 plus and minus the square root of 9 minus x. We can see the 3 in the middle. We should have known that was coming. And then we're going to have plus the square root and minus the square root. So it looks like y2 is 3 plus the square root. And y1 is 3 minus the square root. So we can see that the 3's cancel, and our height is a square root of 9 minus x minus a minus square root of 9 minus x, 2 square roots of 9 minus x. This is the complication that we had to deal with in this particular situation. But now we can refine the volume of our slice to be 2 pi times the radius. The radius is 2 plus x. Times the height, which is 2 square roots of 9 minus x. Times our delta variable. Now that I've got the volume of the slice entirely in terms of the delta variable, we're done with the development phase. Next up is to write a definite integral, which will represent our total volume. We add up all such slices and let the number of slices go to infinity. So our V total. I'm going to factor out a 2 pi and a 2. So I'm going to factor out the 4 pi. I'm going to leave this as 2 plus x. Oh, there's nothing to simplify. So I'm not doing anything. I am going to make sure that my discrete delta x becomes a nice continuous dx. And the x values that are in play, the region starts when x is equal to 0 and ends when x is equal to 9. So we'll integrate from 0 to 9. Now we have completed the definite integral phase. Mainly it's about figuring out the interval over which you're integrating. Remember, we're not integrating from -2 to 9 because there's no region from -2 to 0. The region starts at 0 and ends at 9. These are the x values that were in between. Now we'd have to integrate this, which would be a substitution. W equals 9 minus x. That sounds like a lot more work that I'm willing to put in. So I'm just going to 4 pi math 9, 2 plus x times the square root of 9 minus x. Close the square roots. That's good. With respect to x from 0 to 9. Oh, and I included the 4 pi this time. That's amazing. 1266.7, just like we had before. Since our values match for both of them, we're pretty sure that we're correct. If these two values did not match, one of them is wrong. That doesn't mean that both of them are wrong. It doesn't mean that one of them is right. It just means that one of them is wrong. One of them being wrong includes both being wrong. If you're in a disagreement and one of you is proven to be wrong, that does not mean the other person is right. It's also possible that you land on the exact same answer and it's still wrong. It could be really weird. Any questions? I don't know which of these you thought was easier. I personally like slicing into shells, even if it involves having to invert a non-invertible function like you had to do here and coming up with two values. Mostly because on this particular problem, it was just a parabola. Now, if I had drawn like a sine, if I had written x equals sine of y, I might have reconsidered and just done perpendicular. But it wouldn't be impossible. Always know that if you have a well-defined region and you know what the axis is, both techniques will work just fine. It just depends on what complications you want to deal with. In the washers, we had to deal with the two different radii. So we had to deal with that hole in the solid. So it's more of a but dealing with that has been baked in to the fact that we like to use pi times r squared minus r squared times the delta variable. On this problem, on this version, using this strategy, the complication was that we had to invert a not invertible function. We had to come up with those two y values. So in the previous problem, we're looking at a washer. So pi r squared minus r squared. If we look at the top view of the slice, if we look at the top view of the slice where our axis of rotation is here in the middle of a gap, we have two different radiuses. We've got the inner radius. That's the radius of the hole. That's the radius of the gap. And we've got the outer radius. That includes, the outer radius includes that hole. So we need to subtract the gap. We need to subtract the hole. So we're doing a pi r squared minus pi little r squared. So this is the whole circle. So we take the entire circle and subtract the circular hole in the circle. So pi r squared for the whole circle minus the circle inside. And so when we write this, I usually just factor out the pi. So I don't have to write so many pi. Note that we didn't have to do that when we were slicing parallel to the axis of rotation. We selected where the hole is when we slice parallel by choosing our x values correctly. So the hole is there because my axis of rotation is 2 plus x. Think of our radius as 2 plus x, but we only integrate when x starts at 0. So that's creating the hole when we slice parallel. Slicing perpendicular, we had to have the hole as part of our calculation. How's everybody okay? Now, I know that everybody's watching these problems saying, I can see how important these problems are. I know that on our mission to Mars, we will definitely be having to do these calculations by hand. They left that part out of the movie Martian, and they instead had the part where he's like throwing potatoes and poop so that he could eat, and not the part where he's calculating volumes of solids of revolution. But I'm sure that was an integral part of his survival on Mars. Has anybody seen that movie, Martian? It's just another movie where we have to rescue back in. Matt Damon gets stranded on Mars. And so it becomes a kind of survival movie. All right, that's going to do it for today. That's going to do it for this week. I'll be doing office hours tomorrow at the normal time from 9 to 11. So I'll be on my personal Zoom. I'll post the link in case anybody's missing that. Everybody have a good weekend. I'll see y'all on Monday, and thanks for playing.